All right, hello everybody. We're going to be going over the growth tables, graphs, and evaluating equations. This will help prepare you for Friday's test. So here's the first problem. Y equals 2 to the power of x. We need to graph that. Recognizing this is definitely exponential growth. So what we're going to do is we're going to complete the table, knowing that this is a function or an equation that we can plug numbers into. So if we plug in 0, for example, 2 to the power of 0. Do you remember what 2 to the power of 0 is? Right? What about 5 to the power of 0? Or 10 to the power of 0? Right? Anything to the power of 0 is simply 1. So if we multiply 2 to the power of 0, or get that, it's going to be an output of 1. What about 2 to the first power, which is this one right here? That's 2. 2 to the second power, that's 4. You'll notice that there's a pattern of multiplication, right? It's going to be multiplying by 2, multiplying by 2. So how would we work backwards? This is where negative exponents do tend to get a little weird. What if we took 2 to the negative first power? What would you get? Let's see. 2 to the negative first power. We get 0.5. Why? What's the opposite of multiply by 2? Right? Working backwards, we have to divide by 2, giving us 1 divided by 2 is 0.5. Now, if we divide that in half again, we'll get 0.25. Let's confirm that just by using the negative second power. 2 to the negative second power is, let's see, 2 to the negative second power. It's 0.25. So with these values, we can go ahead and give a rough graph of the equation 2 to the x power. Negative 2 comma 0.25 is about there. Negative 1 comma 0.5 is about there. 0 comma 1, which is the y-intercept. 1 comma 2, 2 comma 4, and you can actually realize what's going to be the next number if we keep multiplying by 2. It's going to be 4, then 8. And that is enough information to graph roughly what this equation looks like. What's the multiplier? We notice the multiplier is 2. Now is a chance for us to learn a little bit of a trick. If we press the y equals button, do you like tricks, by the way? Yeah, we're going to use a trick. So if we press the y equals button, we can actually use the equation and our graphing calculator to our advantage. Watch this. Enter the equation 2 to the power of x. 2 to the power of x. Right there. Press graph. You'll see that a graph or a function actually appears there. This is not enough detail, but you can see that it does match the graph that we did. That's good news. But what if we can actually come up with a table in a matter of seconds? This is where it's huge to have a graphing calculator. Watch this. If I want to access the table, you see where it says graph? Right on top of the word graph is the word table. I want to access that blue button. So I'm going to go ahead and press second, the blue button, graph, to access the table. Look at how this table matches perfectly with the table that we created, even giving us the next number of 8 and the following number of 16. You can imagine what's after 16. Let's check. Keep multiplying by 2. What would we get? 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. 16 times 2. But Mr. Maynard, it's not showing. How do I make it show? Look. Press the down button. You can get as many numbers as you possibly could want just by going down up the list. This is huge. Why? Because we have another problem that we need to solve. Let's use this trick to solve number 2. Press y equals. Delete that equation. Let's type the next one. The next equation is 4 to the power of x. Again, if you're lost, which I would be sometimes, it's okay. Press y equals. Press 4 to the power of. Power of is right here. This button right here. 4 to the power of x. Now you can look at the alphabet and type x if you want to. Otherwise, there is a really, really convenient x button right there. So 4 to the power of x is the equation. Now, what do I want? Do I want the graph? The graph is not detailed enough. As you can see, it looks pretty much identical to this one. What we really want is the table. How do I get to that table? Exactly. You got to press the blue button to get to that table. And look at all these values, all these numbers that we can just put into our table. Now, remember, what is 4 to the power of 0? 4 to the power of 0 is 1. What is 4 to the power of 1? 4. What is 4 to the power of 2? 4 squared? 16. But this table gives us all the numbers we could need. So we're going to go ahead and input these numbers into our table as well. 0.0625, negative 1, comma, 0.25, 0, comma 1, 4, 16. As you can see, we have a starting value of 0, comma 1 and a multiplier of 4. Now, did you know that I could put a 1 in front of this equation if I wanted to? That's my starting value. What's my starting value here? I could put a 1 in front there. That's my starting value, 0, comma 1. What do you think the starting value of this one is? We'll get to that very soon. Let's graph this first. 0, comma 1, negative 1, comma 0.25. It's getting really, really close to 0. As a matter of fact, it gets super, super closer and closer to 0, but it never reaches 0. As you can see on this list, the numbers get very, very small, but it's never actually 0. Okay, let's keep graphing. 1, comma 4, 2, comma 16, which that one doesn't fit on our graph. That's why we're just going to put a little bit of a arrow to indicate it goes on forever. Next problem. Problem number, well, this is 2. This is also 2. Here we go. Problem number 2. Okay, let's see. Let's go ahead and do 3 times 2 to the power of 0. Just to do this problem right there. The starting value. What is 2 to the power of 0? 1. And what is 3 times 1? 3 times 1 is 3. So if you put in 0 into this equation, you get 3. That's our starting value. It's the number there. It doesn't matter. Whatever number is in front of the equation is the starting value. So as you can see, the starting value here was 1, 1. The starting value here was 1, 1. The starting value here was 3, 3. Let's use our graphing calculator now to get the rest of the numbers. By the way, actually, if the starting value is 3, what's the multiplier? Right there. We can use the multiplier to get all the other numbers. 3 times 2, 6. 6 times 2, 12. Work backwards, and we can get the other numbers as well. but I'm going to use my graphing calculator. Y equals, type in the equation, 3 times 2 to the power of x. Table. And there we go. We have all the numbers we could need. Negative 2 says 0.75. Negative 1 says 1.5. 0, 3, our starting value. By the way, I actually made a mistake here. What does it say? What's the y-intercept? We need that to be a coordinate. So I'm going to go ahead and change that to 0, 1, right there. 0, 1, right there. And this one is actually going to start at 3, 0, 3. Okay. What's the multiplier? We know the multiplier is 2. Every time it's getting bigger by 2. So let's graph all these points. Negative 2, 0.75. Negative 1, 1.5. 3, 6, 12. That one doesn't appear to fit. But we know that the numbers are getting closer and closer to 0 here, and closer to infinity over here. Now it says observations. What pattern do you notice on all 3 tables? Answers given to us. The y values increase as the x values increase. They're going up. It's increasing. What is the shape of all 3 graphs? We can say it has sort of like a J shape. A J shape. Or you can say that it is nonlinear or exponential. What do you notice about the multiplier or common ratio? What do we notice? All of the multipliers are positive. Or you can say greater than 0, meaning it's going to be increasing. Okay, now let's go ahead and go to the below and complete this portion right here. So under f of x, I want you to write, you could write y equals. It's the same thing as a function, but we like to name them different things sometimes. So we like to call this one f of x. The next one could be g of x, etc. But we're going to call this the end value, if you'd like to. The a is the starting value, or the y-intercept. The b is the multiplier, or common ratio. And x, we can consider it sort of like every x, every time it goes up, it's going to be perhaps a stage or time. Factors like that. So if you have like 5, you can say, oh, that means 5 years. After 5 years, here's where my money is. So let's go to this problem right here. Does the equation 6 times 4 to the power of x model exponential growth or decay? Well, let's answer these questions. 6, what's the initial value? 6. It's our first number. What's the growth? 4. What's the end time if x equals 2? Let's plug in the number 2. Substitute x for 2. 6 times 4 squared is 96. What is the end time if x equals negative 2? 6 times 4 to the power of negative 2. Just like this in your calculator. It says 0.375. And this page is done. Remember, you can do positive exponents, you could do negative exponents. They will give you the answer. The calculator will give you the answer. You can also use patterns to find out whether it's multiply or divide if you're going backwards. So moving forward, positive exponents. Moving backwards would be our negative exponents. All right, let's go ahead and flip over to the next page. This next portion asks us to identify whether something is linear, which is a straight line, whether it's growth, or whether it is decay. So exponential can be growth or it could be decay, whether it goes up or down. This first one is going to be linear, straight line. The second one is growth. Third is growth. And the last one is decay, meaning it's sort of dying out, getting closer and closer to what appears on this graph, 20. Number 6, which graph matches the equation 1/4 times 2 to the power of x? Well, let's answer these questions first. Is this growth or decay? The growth factor is 2. The initial value is 1/4. Let's see what this next part is. The growth is still 2. It's not very different. And finally, what is the ending time when x equals 4? So if we plug in or substitute 4 into our equation, what would we get? So I'm going to write 1/4 as 0.25. And let's see what number it comes out. It appears the output would be 4. So let's look for the coordinate 4, 4, and let's see if it matches any of these graphs here. Because if we plug in the number 4 as our exponent, we input 4, output is 4. Let's see if 4, 4 is on any of these. This is the only one that has 4, 4 on it. The second thing that we can notice is which one has a starting value of 1/4. Starting value is your y-intercept. So which one has a y-intercept of 1/4? This is the only one that has a y-intercept of 1/4, or very close to it visually. So the answer is definitely A. Moving on. We must write an equation based on the table and also figure out some other numbers here. So right away, we can start out and find out the initial value. It's 8. The growth is how fast is this thing multiplying. So it looks like we can see the number is 8, then 24, then 72. So you can see that this is times 3. Otherwise, use the trick. 24 divided by 8. 24 divided by 8 is 3. So that's our growth factor. So we can go ahead and say 8 times 3 to the power of x. Now we need to calculate the fifth one, so 8 times 3 to the power of 5. Calculator, 8 times 3 to the power of 5 is 1944. The calculator tells me that answer. Now what you can do is you can check your work, see if it actually matches up with your table. You can go to y equals and type the equation. 8 times 3 to the power of x. Table. And see that these numbers match perfectly with our table. Actually gives us the fifth number as well, 1944, as our answer. So these answers are perfect. Okay, next one. Initial value is 0, something, so 0, 3. We can do this one as well at the same time. What's the initial value of this table? Okay, 0, 0.625. Okay, here is the growth. What's the growth? What's it being multiplied by each time? If you know what 3 times something is 21, you know the answer. Otherwise, we can use the trick. 21 divided by 3. 21 divided by 3 is 7. So the growth factor is 7. These numbers are being multiplied by 7 each time. We can confirm our answer by multiplying 21 times 7. 21 times 7.
It's 147.
We can even go backwards. 3 divided by 7.
The answer is approximately 0.4285.
And that is a match. So that's our values. So we're going to say the equation is 3, our a value, then our b value to the power of x. Calculator time. What happens if you plug in the number 5 or substitute the number 5? 3 times 7 to the power of 5. 504, 21. 504, 21. All right, next equation. This one is going to be a growth factor of something. I don't know what this number is times something is 5, but I do know what 5 times something is 40. All right, 5 times what is 40? Otherwise, use the trick. 5 divided by 0.625, or 40 divided by the previous number, 5. What do we get? 5 divided by 0.625, that's 8. So the multiplier is 8. Let's check 40 divided by 5. What is 40 divided by 5? It says it's also 8. Multiplier is 8. So let's write the equation. The initial value, which is a, is 0.625. The multiplier, which is b, goes in parentheses to the power of x. Now, if we want to find the fifth value in this table, we could keep multiplying by 8 if we want to. Keep multiplying by 8. Why not? Let's try it. 40 times 8 times 8 times 8 times 8. We can keep going and figure out what that is. But let's just put in the number 5. Typing that. 0.625 times 8 to the power of, we want the fifth one, so fifth power. That's going to give us a value of 20,480. Why are these numbers so big? Because we keep multiplying by 8. If we keep going further and further and further, these numbers are going to get huge. So this part right here is the you try problems. You want to try these problems right here. And be sure to check your